Assalamualaikum warahmatullahi wabarakatuh. Okay, today I'm going to continue discussion on new topic 4, acid-base equilibria. Okay, acid-base equilibria. In your book, is chapter 18 in your textbook. Okay, this delicious picture. All right, tell us something within it that discuss about acid and base application in our life. Okay. We use acid to get the taste of sour. For example, we use lemon. Right? If we want to have a lemon taste, so lemon itself is have acidic properties, right? Whereas to get the muffin become expand in this way, look delicious, they use base like sodium hydrogen bicarbonate. So this widely used in our life. Okay, acid and base applied. In see table 18.1, some common acid and base and their household use: acetic acid for flavoring, citric acid for flavoring. This is lemon juice. Ascorbic acid, vitamin C, nutritional supplement, aluminum salts in baking powder with sodium hydrogen carbonate. Okay. For bases, we use, for example, soda aside, oven and drain cleaner, right? Ammonia for household cleaner. Sodium hydrogen carbonate also as a baking soda, a rising agent in cake mix. Baking soda, mild antacid, we use also for overcome the problem of gastric problems. We use mild antacid, which part of the chemical is base, sodium hydrogen carbonate, and so on. So on and so forth. All right. Okay. Acid base in water. All right. Most laboratory work with acid and base involve water, as do most environmental, biological, and industrial application. So for acid and base to react properly, both of them must involve water as their solvent in aqueous solution. All right. In chapter 4, actually you discussed already in chemistry 1. Chapter 4 in this book. The water is the product in all reaction between strong acid and strong base. Okay, all reaction between acid and base produce water. Okay, as a product. Okay, we can see which of the net equation here. Okay, if we look at the equation, right, HX stands for acid and OH stands for base. All right, then as the reaction occurs, MX form. So MX is the salts and water. Okay. All right. So water is the product in all reaction between acid and strong acid and strong base. Okay. That is molecular equation. If we break it down to form total ionic equation, so we have this equation. All right. We break down all the aqueous. Okay. All the aqueous we break down except the H2O. H2O is not the aqueous. H2O is liquid. All right. So to get the net ionic equation, we cancel all the spectator ion here. What is the spectator ion? X minus, M minus. All right, because at reactant it aqueous and the product remain as aqueous. All right, so therefore we cancel the net ionic equation and the spectator ion. We get the net ionic equation: H plus aqueous plus OH minus form water. So this is basically the ideas of reaction between strong acid and strong base, which is actually we produce water. Okay. Right. Okay, now let's focus on the acid itself. Okay, it's not before this is neutralization. Okay, now take the acid itself. We discuss the acid properties of acid. Okay, when we take a compound that is can dissociate in water, all right, to form H plus, So then the compound itself become acidic when it in water. Okay. For example, we take, this is general equation. General equation, take the acid either as in a gaseous form or liquid form. So acid, okay, usually it is molecule in the form of molecule, HA molecule. For example, we take HCl. HCl at the first moment before react with water, before we put in water, HCl is hydrogen chloride. Okay, hydrogen chloride. It form a covalent compound like this. And this is general of HA, right? HA. So it's a molecule, similar like hydrogen chloride. Okay, when you put in water, hydrogen chloride itself is a gaseous. Hydrogen chloride is a gaseous. All right. So here in general, any acid compound, HA, gas or liquid, when it react with water, put in water, all right. So dissociation occurs. Dissociation of HA occurs. Okay, HA it has a covalent bond between them. All right. So when it put in water, the covalent bond break. How many electrons involved for one covalent bond? 2 electrons involved. So these 2 electrons both gained by the A. They become lone pair. So you can see another lone pair exists here. Alright. So another lone pair it comes from the bond broken. The bond broken. So that they have one lone pair. So now on the A they have 4 lone pair in this case. That's why they become negative ion. Again, extra electron. Negative ion. Okay. So so therefore then in this case, but as the two electron gained by the bond broken, 2 electron gained by the A, H here become H plus. H become H plus. We call it as proton because no electron at all on hydrogen at this moment. So what present on the hydrogen? Proton. Subparticle present, proton. That's why H plus means when you see proton, the words proton itself here refer to H plus because H plus only subparticle present is proton. Okay, so as the bond break, H plus form. Okay, this H plus highly attracted to the water molecule. Highly attracted to this water molecule. Alright, this water molecule. Okay, so what happened? As it is highly attracted, one lone pair of the oxygen. Okay, one lone pair of the oxygen used to form bond with the hydrogen. So actually like this. One lone pair used to form bond with the hydrogen. So therefore, the product from this, right, it form hydronium ion. Hydronium ion. This is the molecule. All right, hydronium ion molecule. Okay. This is the hydrogen. Let's say this is the hydrogen. This is the hydrogen from the HA. So this is the H plus. So H plus form bond with the oxygen. Then you have this hydronium ion. Okay, this electron come from this bond. The 2 electron used here is both from the oxygen. Right, one used to form bond with the hydrogen. So this is we call hydronium ion. H3O plus. Okay, so previously maybe your discussion when discuss about acid, it produce H plus, right? So when H plus form, that is acidic. Okay, yes, we can accept as that way too, right? Then actually the discussion is extended. H plus actually react with the water molecule to form H3O plus. This is also acidic. This is also acidic. Acidic. Okay. All right. Arrhenius base acid base definition. Okay, this is just I go straight. Arrhenius base definition, which classify the substance in term of their formulas and behavior in water. An acid is a substance with H in its formula. Right? An acid is a substance with H in its formula that dissociate in water to yield hydronium ion. That is definition, Arrhenius definition for acid. Alright. Arrhenius definition for base. A base is a substance with hydroxide in its formula. That dissociate in water to yield hydroxide ion. Okay. So, kalau case acid just now, an acid with substance with H in its formula. So many acid contain H in its formula. Alright. HCl, HBr, hydrobromic acid. Alright. Sulfuric acid, H2SO4. Phosphoric acid, H3PO4. Right. So they can classify as Arrhenius acid because its formula have H and dissociate in water to yield hydronium ion. So this their H can dissociate to form hydronium ion. For base, must have hydroxide ion in its formula. For example, sodium hydroxide ion, sodium hydroxide, potassium hydroxide, barium hydroxide, magnesium hydroxide. So in its formula have hydroxide that dissociate in water to yield hydroxide ion. So their hydroxide can dissociate from the molecule, then they form hydroxide ion. Okay. Alright. Okay, variation in acid strength. The acid dissociation constant Ka. Okay, variation in acid strength. Okay, acid similar same to base are classified by their strength. The amount of hydronium ion for acid or the hydroxide ion produced per mole of substance dissolved. In other words, by the extent of their dissociation into ions. Okay, all right. Because acid and base are electrolyte, their strengths correlate with electrolyte strength. Strong electrolyte dissociate completely and weak electrolyte dissociate slightly. Okay. For strong acid, alright, of course dissociate completely. For weak acid, it dissociate slightly. Alright, similar to base. Okay, for strong acid, point number 1. Strong acid dissociate completely into ions. Okay, like this. Okay, you look this figure 18.1a. Alright. Before dissociation, relative number of mole of HA, maximum. Alright, 100%. For strong acid, as put in water, alright, put in water, dissociation occur completely. After dissociation, you can see no more HA. Okay, no more HA. The hydronium ion concentration maximum and A minus, right, also maximum. Similar to strong base, right? Similar to strong base. So completely dissociate, right? Completely dissociate to form hydronium ion and A minus. All right. So therefore, when dissociation occurs, HA molecules are no longer present. All right, no longer present. Hydronium ion concentration, which is equal to concentration of A minus, because both maximum just now. So in other words, HA at equilibrium is almost zero. Almost zero. So when we write QC, back to the discussion of equilibrium, right? QC equal to hydronium ion concentration times with the A minus concentration divided by HA time with the concentration of H2O. Alright. Since H2O is 1 because pure liquid remain unchanged. H2O is 1. So QC, HA, concentration of A is close to 0. We say completely 0. So therefore, at equilibrium, QC is equal to Kc, which is extremely large. Extremely large. So Kc is extremely large as the strong acid dissociate completely in water. Okay, because the reaction is essentially complete, we usually don't express it as an equilibrium process. Rare, we don't write for the dissociation of strong acid or strong base. We don't write it in equilibrium. I mean reversible errors. We don't write as zero. It is just irreversible errors, one direction of error. So for example, right, you can see nitric acid react with water, right? So you find one direction errors because we say completely react. So hydronium ion and nitrate ion occurs. Whereas for weak acid, it is dissociated slightly into ions in water. Okay, if you write the equation, kalau this is weak acid, Ha weak acid react with water, it form hydrogen ion 2 and A minus. However, because it is slightly dissociate, we use reversible errors. That means the process can form equilibrium. Forward reaction and direct backward reaction at the same rate. You can see these figures. For weak acid, right, before dissociation, maximum concentration of weak acid. So in the present, when you put in water, so it react with water, but you can see after dissociation, only small dissociation occurs. Small dissociation occurs, that means hydronium ion concentration also small concentration or number of mole, similar for A minus, small concentration. So for weak acid, similar to weak base, it is form equilibrium. Very little dissociation, most of Ha molecule remain intact, remain as a Ha molecule. No break of bond, covalent bond between H and A, mostly. Very little dissociate. That is happen for weak acid. Okay, so weak acid dissociate slightly into ion in water. Alright, so if we write the equation, okay, for example, we take a weak acid here, hydrocyanic acid, as example of weak acid. Hydrocyanic acid, HCN aqueous react with water, form H3O plus and Cn minus. So at equilibrium, for weak acid, because hydronium ion has Cn minus ion concentration, relatively very low concentration compared to HCN. Okay, water, as you said, is pure liquid equal to 1. So here you can say QC equal to KC at equilibrium, which is relatively very small value. Shows that it is very weak. Okay, so at equilibrium, KC is very small for weak acid. Compared to the strong acid, KC is very large. Because dissociation occurs, create very high concentration of hydronium ion and A minus. Okay. You can see this figure. Alright. This is a reaction between zinc and the comparison, the make comparison. Concentrate zinc strips immersed into strong acid 1 molar HCl. Another test tube, a zinc strip insert into a weak acid 1 molar acetic acid. Alright. So you can see the difference here. Alright, acid react with metal produce. What they produce as acid react with metals? The bubble here. This bubble represent what compound? Anybody can answer? What bubble is this? Zinc immersed in acid. So reaction between zinc and acid produce this bubble. What bubble is this?
Hydrogen gas.
Okay, this is hydrogen gas. Alright. So what's different between test tube, first test tube and second test tube in terms of the hydrogen gas? You can see clearly, right? More bubble present for the strong acid compared to weak acid. Because hydronium ion, the presence of hydronium ion is very large in the strong acid compared to the weak acid. Alright. So means here, if we say interreactivity, strong acid react faster than weak acid. Since the hydronium ion concentration is greater present in the strong acid. Okay, all right. So just now we write Kc expression, right? Qc and Kc expression for weak acid. Basically for a weak acid, because strong acid is extremely large, right? So the discussion of Kc is more on the weak acid. Okay. We can write the specific equilibrium constant for acid dissociation. We can write. That only includes species whose concentration change to any significant extent. Okay. All right. This equation. Ha react with water, produce hydronium ion and A minus. This is general equation, general equation of acid dissociation. Okay, this is for weak acid. Right. So what we discuss now is weak acid. We not discuss the strong acid because strong acid Kc is extremely large. So straight direction complete. Now we focus on dissociation of weak acid because the dissociation is not complete, relatively small. All right. So we can write the Kc expression again. This is we discussed already before. So Kc equal to hydronium ion concentration times the A minus concentration divided by Ha and H2O. Alright. Okay. Since the concentration of H2O remain unchanged, because this is pure liquid, alright, the discussion here you can read. Alright. So this is H2O is pure liquid. So H2O is equal to 1. We take it as 1 the concentration. So we are Kc we bring the H2O here, we alter the equation. So Kc times 1 represent the concentration of water equal to Ka. So this is the new, new equilibrium for acid dissociation. We say as acid dissociation constant, Ka. Right. So here we talk more about Ka, not Kc lah, in the equilibrium of acid. We take about Ka. A stand for acid. Okay. Ka equal to hydronium ion times the concentration of A minus. Okay. Hydronium ion times divided by the Ha. Alright. So you look here. What is the relationship between Ka value and hydronium ion? Directly proportional or inverse proportional? Ka and hydronium ion concentration. I want to ask. Directly proportional. That means if the Ka value high, hydronium ion concentration high. Similar, if hydronium ion concentration is high, that means Ka is high. If hydronium ion concentration is low, that means Ka is low. Similar, if Ka is low, that means hydronium ion concentration is low. Because it is directly proportional. Okay, so Ka here is for weak acid. Ka for weak acid. So like any equilibrium constant, Ka is a number whose magnitude is temperature dependent. Temperature dependent, of course, because equilibrium is dependent on temperature. And tell how far to the right direction has proceeded to reach equilibrium. Of course, if it is more, you can see the stronger acid, not strong acid. The word stronger too means strong within the weak. Strong among the weak acid. That means stronger acid. Stronger acid, the higher the hydronium ion concentration at equilibrium and the larger the value of Ka. Like that. Stronger weak acid lah mean. Stronger weak acid will have a higher hydronium ion concentration and the value Ka also larger. Stronger acid, higher hydronium ion concentration, larger Ka. Weaker acid, when we say weaker acid mean lower hydronium ion concentration, smaller Ka. Smaller Ka. So we can rank the weak acid ni according to their Ka values. What we discuss now among the weak acid, we exclude already the strong acid because strong acid is a completely dissociation. Now we discuss about among those dissociate not complete dissociate, slightly dissociate. So the range of Ka values, you can see lah. Some benchmark for Ka values for typical weak acid give an idea of the fraction of HA molecule that dissociate into ions. For weak acid with a relatively high Ka, okay, if you have a value times 10 negative 2 at 1 molar solution, so this is considered weak acid, stronger weak acid. We say stronger weak acid. The Ka of chlorous acid, for example, chlorous acid is 1.1 times 10 negative 2. So this is considered stronger weak acid. Okay, and 1 molar HCl chlorous acid, 10% dissociated. Okay, so that is for chlorous acid. For weak acid with a moderate Ka, 1 molar solution is around 0.3% of the HCl molecule dissociated. For example, Ka acetic acid. Acetic acid cuka is 1.5 times 10 negative 5. This is the Ka value. This is considered moderate. 1 molar of acetic acid is 0.42% dissociated. Okay, for a weak acid with relatively low Ka, this is around 10 negative 10. 10 negative 10. Okay, so that is the solution has only, for 1 molar solution, this is around 0.01% of HCl molecule dissociated. Okay, 0.001%. So the Ka of HCl is at 6.2 times, for example, Ka value for HCl is 6.2 times 10 negative 10. So 1 molar HCl is around 0.025% dissociated. So you can see, if with 10 negative 2, this is considered stronger weak acid. 1.8 times 10 negative 5 times negative 5, it is around moderate weak acid. 6.2 times 10 negative 10, this is considered as 10 negative 10. 10 negative 10 is considered as weaker weak acid. So weaker weak acid, lower percentage dissociation of A, smaller Ka. Okay, this is table. Ka value for some monoprotic acid at 25 Celsius. Monoprotic means they have one hydrogen. That means monoprotic. H. Right, one H. One dissociated H. One dissociated H. Okay. For formic acid, you see two hydrogen, right? But the hydrogen dissociate from the formic acid only this hydrogen, not this hydrogen. This is considered one monoprotic acid. Okay, so you can see, okay, Lewis structure shows that this is the red colors represent the hydrogen that dissociate from the molecules to form H+. Okay, and combine with water form hydronium ion. Combine with water to form hydronium ion. Okay, so that represented by the red colors. You can see the Ka values. You can see, for chlorous acid 1.1 times 10 negative 2, nitrous acid 7.1 times 10 negative 4. This is decreasing the Ka values. Decreasing. Alright. The lowest here among this is 6.2 times 10 negative 10, hydrocyanic acid. So you can see, from below to above, acid strength increase. Mana Ka high. Ka high mean hydronium ion concentration higher lah. Ka higher, hydronium ion concentration higher. Ka lower, hydronium ion concentration is lower. Back to this just now. Faham ni? Okay, back to this. Right. Ka high value, that means hydronium ion concentration high. Ka low mean hydronium ion concentration low. Okay, alright. Okay, in the books you can read this, classifying the relative strength of acid base, strong acid, weak acid, strong base, weak base. Please have a look on this. Alright, so that you can get have ideas which acid considered as strong acid, which acid considered as weak acid. Alright, for example, I take one example, strong acid, hydrohalic acid. This is considered all strong acid except HF. HF is weak acid. Alright. Oxo acid, for case oxo acid means contain oxygen. The acid contain oxygen. So if the oxygen exceeds the number of ionizable proton by 2 or more, alright, then it is considered as strong acid. For example, HNO3. H, 1 hydrogen, oxygen 3, right? 3 minus 1 equal to 2. So means 2. So it's considered strong. 4 minus 2, 2. Considered strong. 4 minus 3, minus 1 equal to 3. Considered strong. Alright. Phosphoric acid, H3PO4. That is considered as weak acid because H3, 3 hydrogen, oxygen 4. 4 minus 3, 1. So phosphoric acid is a weak acid. Understand? Right, so please have a look on this so that you get ideas to classify acid and base. Alright, I think I stop here.